You ever hear a claim and just think to yourself, is that really true? Well, today we're going to crack open a super powerful statistical tool that lets us play detective with data. And don't worry, this isn't your boring high school math class. This is all about putting claims on trial and making decisions based on cold, hard evidence. So let's open the case file.
Okay, picture this. You go to the store, you buy a can of Hilltop coffee. The label promises you're getting at least 3 pounds of coffee. But lately it feels a little light. Is that just in your head, or is something kind of fishy going on? This is the exact kind of problem that hypothesis testing was designed to solve. And this is going to be our case file for today.
All right, so we have a claim from the company, and we have our own suspicion. We can't just go on a hunch, right? We need a process, a structured investigation to figure out if there's enough evidence to actually challenge what the company is saying. So let's start by identifying the suspects. In any good courtroom drama, you've always got two opposing sides, right? The prosecution and the defense. Well, in statistics, it's pretty much the same thing. We have two competing ideas, two hypotheses that are about to go head to head. This slide right here just lays out our courtroom drama perfectly. On one side, you've got the defendant. This is our null hypothesis, which we call H0. Think of it as the status quo, the claim that's already out there. And just like in court, it's assumed to be innocent until proven guilty. Then, on the other side, you've got the prosecution. This is the alternative hypothesis, or HA. This is the new idea, the challenger, and it's got the burden of proof. It has to make the case. So, the null hypothesis is our starting point. It's the world as we know it, the existing belief. It's the nothing new is happening here hypothesis. For our coffee company, the null is simply their claim that the average can of coffee has at least 3 pounds in it. Simple as that. The alternative hypothesis, though, that's our theory. It's what we, the investigators, are actually trying to prove. It's the direct opposite of the null. It's our suspicion, our claim, that the company is actually underfilling the cans. Okay, so let's put it all together for our Hilltop coffee case. It looks just like this. The null hypothesis, H0, is the company's claim. The average weight is greater than or equal to 3 pounds. Our suspicion, the alternative hypothesis, HA, is our challenge to that. No, we think the average weight is actually less than 3 pounds. The battle lines are officially drawn. With our suspects all lined up, it's time to move to the next phase of the investigation. We need to go out and gather some solid evidence. Now, obviously, we can't go out and weigh every single can of Hilltop coffee that's ever been made. That's impossible. So we do the next best thing. We take a random sample. For this case, let's say we gathered 36 cans. We weigh them all, and what do we find? The evidence is in. The average weight of our sample is 2.92 pounds. And this right here, this brings us to the absolute core of the issue. Yeah, okay, 2.92 is less than 3, we can all see that. But is it different enough? Could that tiny difference just be random luck in the cans we picked, or is it a big enough difference to serve as real proof that the company is underfilling? We need a way to measure that. And that's where this thing called the test statistic comes into play. You can think of it as our single most important piece of evidence. It's one number that boils down everything we found in our sample and tells us just how far away our result of 2.92 is from their claim of 3. Okay, we've got our suspects. We've got our evidence. It's time to take this thing to court and reach a verdict. Now, before we even look at the evidence, every court has to set the standard of proof. In statistics, we call this the level of significance, or alpha. This is our line for beyond a reasonable doubt. It's basically the maximum risk we're willing to take of making a terrible mistake, convicting an innocent defendant. A really common standard, you'll see it everywhere, is 5%, or 0.05. So one way we can weigh the evidence is with something called the p-value. Take a look at this graph. The p-value answers a really specific question. If the coffee company is totally innocent, if the average really is 3 pounds, what are the odds we'd randomly pull a sample that weighs as little as ours did? And as you can see, that probability, our p-value, is incredibly small, just 0.0038. So the verdict comes down to a really simple rule, and you can remember this. If the p-value is low, then null must go. A super tiny p-value means that our evidence would be a huge, shocking surprise if the defendant were actually innocent. So surprising, in fact, that we start to think, maybe they're not so innocent after all.
Now, there's another way to get to the same verdict. It's called the critical value approach. This method basically draws a line in the sand, which you can see right there in that shaded region on the graph. If our main piece of evidence, that test statistic, crosses that line, we've got enough to convict. For our coffee case, that line in the sand was drawn at -2.33. And now, the moment of truth. Let's look at the evidence. Our test statistic was -2.67, which blew right past that critical line of -2.33. And our p-value of 0.0038, way smaller than our standard of 0.01. The evidence is just overwhelming. The verdict is in: we reject the null hypothesis. There is very strong statistical evidence to suggest that Hilltop Coffee is, in fact, underfilling its cans. But hold on. Just like in a real-life courtroom, our statistical system is imperfect. Sometimes, even when we do everything right, we can still get the verdict wrong. And it's really, really important to understand how that can happen. This table lays out all the possibilities perfectly. Look, 2 of them are good outcomes, right? We correctly acquit an innocent person, or we correctly convict a guilty one. But there are 2 ways we can mess up. A type 1 error is basically a wrongful conviction. We reject the null hypothesis when it was actually true. And a type 2 error, well, that's when the guilty party goes free. We fail to reject the null when it was actually false. So let's just nail this down. A type 1 error is sending an innocent person to jail. A type 2 error is letting a guilty person walk free. And remember that level of significance, alpha, that we set way back in the beginning? That number is the exact probability that we're willing to accept for making a type 1 error. Whew, okay, we have covered a ton of ground in this investigation. So let's wrap it all up and put everything into a simple, step-by-step investigator's handbook. Here it is, the 5-step process for putting pretty much any claim on trial. Step 1, you gotta state your suspects, the null and the alternative. Step 2, you set your standard for the evidence with alpha. Step 3, go out and gather the evidence, get your sample data. Step 4, weigh that evidence using either the p-value or the critical value. And finally, step 5, reach your verdict. You either reject or you fail to reject the null hypothesis. And really, that's the whole shebang. You've just walked through one of the most important and fundamental ideas in all of statistics. And this isn't just some abstract theory. This is a real, practical framework you can use for thinking critically, for challenging the things you hear, and for letting the data speak for itself. So the next time you hear a wild claim on the news or you see an ad that just seems too good to be true, you now have the tools to stop and ask, okay, but where's the evidence? So I'll just leave you with this one last question. What claim in your world would you want to put on trial?